One application of differentials is to approximate roots. Check how it is done here in differential calculus. What are differentials? These are small values considered as the change or discrepancy from the exact value. Differentials are generated from taking the derivative of the function, and this is modeled as dy, which is equated to the derivative of the function with dx. To apply it in problem solving, approximation using differential is to come up with an approximate y which has a known root or power. Then adjust this y with dy to come close to the actual value. The first problem in this series is to approximate the fourth root of 90. By plugging in keys in the calculator, the exact value of the root is 3.08007. But without a calculator, we can approximate using differential equation. The first step is to identify a fourth power nearest the premise. Think of a fourth power nearest 90 and take it as x. For this example, use 81, as 3 raised to 4 is 81. With 81 covering a big chunk of the approximation, we are left with a discrepancy of 9, which we consider as dx. Compute for the adjustment by generating a function, which is y, also the function of x, equated to the fourth root of x. Complete the working equation by coming up with dy and dx. This is done by differentiating the function. So take the fractional exponential form of the equation, which is y as equated to x raised to 1/4, then differentiate it. Using power rule, dy over dx is then taken as a quarter of x raised to negative 3/4, with dx over dx from chain rule. Dx over dx is 1. So placing back the radicand, dy over dx is 1 over 4 with the fourth root of x cubed. Take the differential of y by cross-multiplying dx to the other side, and come up with dy as 1 over 4 of the fourth root of x cubed multiplied by dx. With all parameters already figured out, we can plug everything in the working equation. Y plus dy is then the fourth root of x plus 1 over 4 times the fourth root of x cubed with dx. Plug in values as identified earlier. Y plus dy is then the fourth root of 81 plus 1 over 4 of the fourth root of 81 cubed multiplied by 9. This is simplified as 3 plus 1 all over 12, which gives the final approximation of 3 and 1/12, or 3.0833, a really close value from the actual root of 3.08007. What if the base root taken was somewhat far from the premise? Say the identified fourth power is 16, coming from 2 raised to 4 as 16. The discrepancy which needs to be adjusted for this case is 74. The function y, which is f of x, is the fourth root of x, and this is differentiated to generate dy and dx. Dy over dx is then 1/4 of x raised to negative 3/4 with dx over dx from chain rule. The last part is simplified as 1. So dy over dx is 1 over 4 with the fourth root of x cubed. Cross-multiply dx and have 1 over 4 with the fourth root of x cubed with dx. Note that this is the same function we have derived earlier, which means this working equation remains the same with whichever approximated values we plug. So continue with looking for the approximation using the general function. Plug in x of 16 and dx of 74, coming up with the fourth root of 16 plus 1 over 4 of the fourth root of 16 cubed, multiplied by 74. This is simplified as 2 plus 37 out of 16, which can then be coined together as 2 and 37 over 16, which is 4.3125. The approximation is rather far from the actual value, as there is a big discrepancy to adjust. Let's try another approximated value, like taking x of 256, as 4 raised to 4 is 256. The discrepancy from this approximation is negative 166 from 90 minus 256. The working equation for this case remains the same as the fourth root of x. The same procedure of taking the derivative is followed, whereby we end up with the function the fourth root of x plus 1 over 4 times the fourth root of x cubed with dx. Place values of x, which is 256, and dx of negative 166. This gives 4 minus 83 over 128, which results to 429 over 128, or that is 3.3516, an approximation which is still far from the actual value of 3.08007. So the key is to approximate the value nearest the premise.